तो जरूरत नहीं हो जाएगा। ओ अच्छा, उसके लिए ठीक ठीक ठीक। हेलो हेलो
हेलो हेलो।
हेलो। Yes, good morning all. So I am Siddarth Arora. I am scientist B at National Institute of Hydrology, Regional Office Guwahati. So today's lecture is on design flood estimation for DPR preparation. Everybody here is a civil engineer by background. Yes. Anybody else who is not a civil engineer? Yes. Which stream are you from? Agriculture. Anybody else? Agriculture engineering. So, yes, sir. So, you have done any theory classes during your bachelor's for flood forecasting, estimation, other methods, distribution methods? You have taken some. So, you have a broad idea. So, anyway, so today we'll go for this. So, let's start with the basic theory. So, a flood is a highly relative high flow system that overtops the natural bank. So, if we say in the simple terms, so you have a river, it has some bank limits. So, when the bank limits are breached, the water flows out of the drainage channels and it inundates the area. So, that is a very typical definition of flood. So, now to prevent all that, yes, please. So, now to prevent all that and take mitigation measures, we develop a lot of structures. We develop weirs, we develop spillways in dams, we make embankment walls. So now all these structures that we are designing and basically putting up in the field, they need to have certain parameters. So we cannot just make a random structure anywhere. So it has to take into consideration that what are we trying to mitigate. So suppose your flood level, your flood discharge, let's say 100 cumex. So you will try to design the structure that can hold the flood level at 100 cumex. You won't design it for 1000 or 50. So we cannot do it at a random pace. So we need to design a structure that mitigates the flood level that we are expecting in that place. So as I told, so why do we need the need for flood estimation? First is that we need to design a required structure. It might be a steep spillway, it might be an embankment, it might be a weir, it might be a diversion channel, it can be anything. Now to construct, design, plan and thing, we always take into account the financial aspects. I think there will be further lectures on this aspect later in this training course. So we always see the economical method, that what is the lowest cost method for our structure. So if we are designing a structure for 100 cumex flood, but the structure is designed for 1000 cumex flood, so obviously the cost will increase manifold. But if we under design it at say 90 or 80 cumex, so our investment will go to waste. So we always need to find a balance. And finally, as the title says, we need to estimate what is the maximum possible discharge and what will be the flood level. So that is the requirement for this. So these are a few types of floods. We have aerial flood. So aerial flood is basically when you have a excess rainfall for a prolonged period of time and all your riverbank channels, they swell up to a maximum value and they inundate the area within the drainage basin. Then we have urban flooding. So urban flooding generally is a term that we can use with interchangeably with waterlogging. So waterlogging generally happens when your urban design is inadequate or the topography has been redesigned in such a way that you find lot of sinks from where the water cannot go out. So we have similar examples in Guwahati. We have seen multiple. I think people who from Itanagar might have seen near Nahara Lagoon that these kind of events do place. Then we have riverine floods, that is topping of the natural banks or the embankment breach is there sometimes. And then we have coastal floods, which are mostly predominantly in the coastal areas, which we don't have to worry about in this region. Now there are multiple methods. to estimate all of these. So one is a rational method, then we have flood frequency analysis, which we'll be looking up in this lecture. Then we have unit hydrograph methods for ungauged basins where we don't have data. And then we have certain watershed models using computer simulations. I think everybody will be familiar with the HEC HMS model, or they have seen it or they might have used it. So these are the few methods where we can do all these kind of analysis and come up with the practical solution. So in flood frequency analysis, first we do is we try to calculate the frequency or the probability of a flood peak. So when we say that the flood is 1 in a 100-year flood, it doesn't mean that that flood will occur only once in a 100 years. It might occur at 2 years difference also. Okay? The 1 in a 100-year flood means that whatever estimate that we have calculated, that this flood level we are designating as 1 in a 100-year flood. So as we start increasing the time period, the what we call observed flood peak will be larger. So 1 in a 10-year flood will be smaller, 1 in a 1,000-year flood will be a much larger. So like if you might have read in the news few years ago, Chennai city was heavily inundated because of heavy rainfall. So that was characterized as 1 in a 1,000-year flood. So that is the way. So it's a statistical term. It does not generally imply that 1 in 1,000 year means only once in 1,000 years. So please keep your mind free on that. So it's a little confusing term, I can understand. Then there are various methods. Either we use log probability graph or we use a linear graph. So we will see the further methods. So what happens is, so once we calculate statistically 1 in 50, 1 in 100, 1 in 200, 1 in 5,000, we try to put it on a graph and we try to extrapolate those graphs to get our desired value. So there are multiple methods. We have Gumbel extreme value, we have log Pearson, we have normal distribution, we have gamma distribution. And this is just a small list. There are multiple more methods than this. So we'll be focusing on Gumbel extreme and log Pearson methods in today's lecture. So these are the most commonly used and most widely used methods within Indian subcontinent. So now I'll be going much more into theory part, so please bear with me. I hope everybody had a cup of tea before they came here. So don't doze off, please. So in Gumbel method, what we do is, so our magnitude of the flood is what we are interested in. How much is the peak magnitude of flood that we are interested in? So it is based on a mean value of the discharge data that we have plus a constant. So this is what we are looking to compute here. So for everything, so 1 in a 1 year 10-year flood, 1 year 100-year flood, so this constant will vary. So how to compute this constant? That is our main aim, so as we can get the desired flood level. So delta x is generally, as I told you, the constant. It is represented by S into K. So S is the standard deviation of the data, whatever data that we have, and K is the frequency factor that has been statistically calculated for different regions at a different. I will just show you how it is. So this is the standard procedure, how to go for it step by step. So please make a note of it. So first thing we do is we take the data, how much data that we have, and we arrange it in descending order. So suppose we have data from 100 to 50. So we list it down from 100 as the first and 50 as the last. Then we assign those ranks to each value. So m equals to 1 for the highest value and m equals to whatever the data number is that we have, that is the lowest value. So the lowest discharge will get the highest m value and the highest discharge value will get number 1. Then we calculate the return period and probability of exceeding the equation by n plus 1 by m and m by n plus 1. So basically t is n plus 1 by m and e is 1 by t. Basically. Any confusion as of now? So m is the rank that we have assigned to the value and n is the total number of data points that we have. So suppose we have 50 data points. So for each value, so for each discharge, so M will be according to the rank and N is the total amount of discharge points. Then after we have done all this, we calculate what is called the square of mean, the mean and the mean of squares. So this term might get confusing. Let me just clarify. So the mean square is you calculate the mean and you square it. Mean of the squares is you take the individual value, square it, and then you take the mean of it. So these two terms sound quite similar, but they are actually statistically very different. So keep in mind that. So mean of squares and square of means. So once you have calculated all this, you calculate the standard deviation. Then from the table of frequency analysis, we calculate the values for our desired return period. So if you are calculating 1 in 50 years, you have a different value. If you are computing 1 in 100 years, you have a different value. So once we have computed all K and S, we just plug into these values. So K value will vary as per our return period. Okay. So once we have this, you can just plot the curve and you can get your desired value. So this is the K value that we are looking at. So for any sample size, 15, 20, 30 up to 100 samples, suppose you have a daily data set. You have a monsoon data set for 3 months. You have 90 values, let's assume. So along with that, based on the return period, 5 year, 10 year, 15 years, that you can use. Now suppose you have 73 data points. So what happens is you have 70 value at 70, you have value at 75. Now I want to compute a 1 in 25 year flood for 73 points. So what I will do is I will take 70 and 75 value and interpolate it linearly to get the amount of value at 73. So it's a very simple method. You have two coordinates, 70, 2.24, 75, 2.23, and you interpolate between these 2 points on a linear fashion. So you can get that value. So that was the theory part. Now let's look at a solved problem. It is a very simple problem. So this I have taken from the DPR as designed by Nehari itself. So this was done for Becky Basin. So we have the data from 1962 to 1982. So we have around 21 data points. So we have the peak flood that we have listed in QMET. So what we did, first you put them in the ascending order. So highest flood was 181, so it gets assigned as number 1. Lowest was 29.6, it gets assigned as 20. So obviously the chronological order will be changed. So we don't have to worry about this, we have to worry about this. So once we have arranged it in a descending order and assigned the rank, we will start calculating the probability and return. Return period is n plus 1 by m. So n is 21, so it will be 22 by 1 is 22. So as we increase the m to 2, it becomes 11. And so on. Probability is 1 by t, so just flip it 1 by x, so we get these values. And this is the square of the discharge. And this is the sum of the squares of the discharge. So once we have these values, now what we need to do, now we have come back to basic mathematics. So first is the mean value. So what is the mean value? Summation of all this by 21. So we get a mean value, that is x bar. Then we need squared mean, that is you take the mean, square it, you get this value. Next step, mean of square. So mean of squares was we squared every value, so this by 21. So you see mean of squares 182,820 by 21 we get. Then we come to standard deviation. So standard deviation is n by n minus 1 into mean of squares minus squared mean in a under root. So we get this value. So now we have S X bar, and now we need to take K. So what is K? K is from the table that has been listed. So you can get it from the CWC tables that are published annually. So for return period we have 5, 10, 20. So X bar is there, S is there, K we have taken from the table direct. So what is KS? K into S, and finally we can get the design flood value. So this is one of the very simple methods. So as you see, as we increase the return period, the amount of peak flood value will increase. So as I told, the larger the time period, the more destructive the flood is going to be. So 1 in a 1,000-year flood is very destructive. 1 in a 5-year flood is not that much. So this is one of the very simple Gumbel method that we use predominantly. It is easy to use, but the only criteria is that you should have the data. If you don't have the data, you won't be able to use this technique. Then we'll come to log Pearson type 3. This is also quite similar to Gumbel method. Instead, we are using it on a log scale. The methodology is quite similar. Just the approach to the problem is a little different. So as in log Gumbel we saw was x equals to x bar plus ks. Here also we are getting a similar formula, but it is in log form. So this is our design flood that is required, qj, y bar, kj, csy. These are constant, mean, and other parameters similar to what we saw in Gumbel. So these are the certain parameters we need to see. So first one is the skewness coefficient, the variance, and skewness. So these are three terms. So don't get confused by it. Don't be afraid of it. These are simple terms. These are all statistical method. So once we have all this, we can just plug it in the equation and get our method. So like we saw in Gumbel method, we have certain table, certain chart. So for a return period or a given probability of accidents, we have various skewness coefficients. Okay. Then finally we come to that whatever calculations that we have done, whether that are correct or not, that we have to test. So we cannot just say that whatever calculations we have done that is correct. We have to prove it that whatever calculations we have done are correct. So we use something called D-index test. So D-index test is the average value of recorded annual peak data. Xi is the ith sample of the first 6 highest values in the series, and Xi is the corresponding estimated value by probability distribution. The distribution having the least D-index is considered as the better suited distribution of PM. So this is, now suppose we are using multiple methods. So each method will give you a different peak value. So Gumbel method will give you a different value, log Pearson will give you a different value, normal distribution will give you a different value. So which value to choose? It's a big question when you have multiple methods. So we have just put it on the D-index test and we use this formula to compute the D-index for the values calculated from the each method. So once you compute, so you cannot just use one single method, Gumbel's distribution, and say this is our flood discharge and we should design it on it. So when you are developing a DPR, you should always take multiple methods into account and then use this one to come up with the most suitable value. Okay. So now that was one set, that how we did if we have a lot of data, if we have a gauged basis. Now suppose we are taking a ungauged basis. So now anybody from Arunachal Pradesh? So as far as I know, Arunachal Pradesh, the data is available only at the locations which is at the Arunachal Assam border. At upper reaches, we don't have much of the data sets that are available, either by WRD or CW. So we can say that it is an ungauged basin. So let's say that we are looking into a Tengadirang Basin in near to Bomdila, West Kameng district. So you have two streams, one is Dirang, one is Tenga. They finally come and meet, and then finally they join the Kameng Basin. Now these two streams, they don't have any gauges, but there are certain events, one in 10 years, I think past 15 or 20 years, there has been twice or thrice there has been minor amount of floods. Now if we want to design any structure like a bridge, yeah, or a small weir, how to go for that? Now we have the streams, but we don't have any data, so we cannot use Gambas method or other method. So what we will use is, we will use something called synthetic unit hydrograph. So everybody knows what a unit hydrograph is. A unit hydrograph. Everybody has read about that? Yes? Yes? So a unit hydrograph is generally developed based on the data that we have available for 1 centimeter of rainfall that we have. Now, we have a 1 centimeter of rainfall, but we don't have any gauge data. So how do we check what is the unit response for that basin? So we will use synthetic unit hydrograph. Now this is a purely empirical based method. That has the empirical method has been derived over a long period based on the observed data from multiple data sets around the world. So first one is the Snyder's method. So in Snyder's method, what we use is, we need duration of effective excess rain, basin lag, peak discharge unit area, base time, and the width of unit. I think everybody has in memory, they might have something called SUH derived when they were doing their courses in BTech, or even masters also. If you are masters in hydrology, they also do that. So this is a very basic system. So you have 1 centimeter of rainfall, and based on the basin characteristic, that is the length of the main stream, distance from the outlet point to a point on stream nearest to the centroid of the watershed. So basically, on the base of basin characteristic, the area, the length, the centroid, and the slope of the basin, we are able to compute a synthetic unit. Right. So what are the parameters? We need to compute W50, we need to compute W75. So W50 is the 50% width of the hydrograph. W75 is at the 75%. We have the peak flow QP that we will compute using this formula, QP into A, and you have all other parameters that you can see. So this is purely a statistical method that you can use, but there is a criteria for it. It cannot be used for large basins. It can only be used for small basins, typically 2,500 square kilometers. So if your catchment area is exceeding 2,500 square kilometers, you cannot use SUH method for your calculations. It will get flagged very immediately when it goes for review. So these are certain numerical methods that you can use, but as of now, because with the time in current days, a lot of data is available. Even at small basins now, CWC has put stations, so you have a lot of data, so you don't need to use SUH, but in case you need to use, this is how we are going to use it. So now coming to, that was theory part. So now coming to the Indian practice. How do we do works in India? So number one, this system, because we are doing it on a SUH basis, it cannot be applied for any catchment which is larger than 2,500 square kilometers. If your catchment is larger than that, you cannot use this. So based on this, India has been divided into around 17 subzones. So 2A, 2B, 2C. This is what the entire Northeast is covered. So 2A mostly encompasses Arunachal, Sikkim Basin, some parts of Upper Assam. 2B includes some parts of Assam, Meghalaya, other things. And C generally mostly considers rivers that are flowing either towards Myanmar or towards Bangladesh. So most of our flood prone regions are lying in 2A and 2. Most of it. We cannot neglect 2C, but the majority flood destruction happens in these two areas. So based on this, so you can always get something called hydrometeorological zones of India, that is published by CWC. So that is CWC 1983 flood estimation report, Directorate of Hydrology for small fish. So the document name. I have shared a QR code. I will be sharing the PPTs with you, so you can just scan the QR code to get this manual. So we need to use this. So I'll just give you a small example. So this is the case of Pagladia River in BTC, in the Bodoland Territorial Council area. So this work was also done by Nehari. So now we have this basin, but we don't have any gauging station in it. But we need to estimate how much flood is going to come, and if we have to design any structure in this, what should be the flood capacity for that. So we have the catchment area is 330 square kilometers. Length of longest stream is 57.3. Then length to the centroid. Centroid is this point. So they compute the nearest mean. And we have stream slope. That's the average stream slope. So what happens is the basin might have a very steep slope at the beginning. It might go gradually, but we are only using the one single value. So based on our synthetic unit hydrograph formulas, we just plug in all those values and we compute all these unit hydrograph parameters. W75, W50 and all this. So as you remember from this. So we have computed all these parameters to develop our unit hydrograph. So once we have the unit hydrograph, we can put our known rainfall on it and get the hydrological response. Okay. So once we have this, so we are using a simple catchment formula, A into D by 0.36 Ti. So this is our estimated net volume of water that is flowing out, that is 1055.6 meters per second. So we need to remember this value. Why? I will just tell you in a. So once we have computed all this, you compute this value for a given catch. A into D by 0.36. So now we have the unit hydrograph, we have time, you have UG ordinate, and we have developed a unit hydrograph in this case. So, but you see, a unit hydrograph is supposed to be for 24 hours. What we have developed is for 29, because our values are full time is coming out to be 29 hours for our unit hydrograph. So we need to readjust because our unit hydrograph cannot be for more than 24-hour duration. So what we do is we use something called isopluvial maps that are published by Central Water Commission. So in isopluvial maps, what they do is they give you a year return period and the amount of rainfall. For 50-year, 24-hour rainfall for northeast area is 32. This is the maximum analyzed rainfall by CWC and a 50-year return period in 1 day. So based on this, we have our point to aerial rainfall ratios that is published by CWC. So our area is 380, which is something coming right here, and we need 24-hour rainfall, so it will be between 88 and 87. So 0.87 value we are taking as of now. So our 50-year rainfall will be 32 into this factor, that is 27.9. So our rainfall for this area at a 50-year return period will be 27.97 centimeter. So these are isopluvial maps published by IMD, as it is also provided by CWC. So you can check all these maps are available in repository. You can request from the requested department and you can get it from there. So you have various. So this is like a 10-year 3-hour map. This is a 100-year 1-hour map. This is a 10-year 24-hour map. Likewise. So whatever return period or frequency that you are trying to compute, you will use the corresponding isopluvial map for that. So basically it just gives you a rainfall value in a 24-hour period that is there. So like for northeast, this is the isopluvial map for 50-year 24-hour rainfall. You have all these contour values. You can check. So most of the Arunachal is little bit empty in this, but you can always extra. So once we have this values, we have the distribution coefficient and the adjustment values. So our catchment we designed from reduced from 29 hours of the SUA to 24-hour design. So these are the distribution coefficients which we can compute. We have the rainfall and we can compute the annual hourly increment. So once we have the rainfall, so now we need to compute is the design loss. Now design loss is the water that we do not that gets wasted away due to overflowing, evaporation, infiltration, other part. So they have defined a constant value. For example, in zone 2A, if we are working in Arunachal and Assam, Upper Assam area, the design loss is described as 0.24 centimeter per hour. So for 1 hour, 2 hour, we have the rainfall data. We just put the design loss, subtract these two, and this is the effective rate. Then for the estimation of base flow. Now base flow is also required to compute. So CWC has given that for zone 2A, you can use it as 0.05 Qmac as the base flow. So final step, we just take everything, add it up and get our SUH at 24 hour, and we can put on the rainfall and we can get our flood peak. So likewise, this is what we have done. We had the time, we had coordinate, we have 1 hour rainfall. Just multiply 1 hour rainfall with the coordinate that we have already computed and you. So this is for Pagladia. You have areas, how much 1 in 100-year flood value will come at different points in the PTC. So whenever you are taking any point, in this case, you need to redesign your catchment. If you are doing it at the near to the confluence of some bigger river, the catchment area will increase. You have to redo all your calculations. If you are doing it a little higher reach, your catchment will change and you will have to again do all your calculations. So like they have done it at 5 different points. So all these process was repeated 5 times. You cannot just take one value and recompute it again and again. Every time you change the point, your catchment characteristics changes and you have to redo all your values. So that's a little technical long method. One more thing that I wanted to tell you. Yes. So the total area under this curve that we have computed and the statistical amount of QTI that we have computed here, this should be nearby. Okay. Ideally, they should be same, but they should be nearby. So if you compute the area under this curve, it will come out to be exactly 105. Our corresponding value is 105.55.6. So it is close by, so we can use it. If this value deviates by a larger amount, you need to redo your calculation. Okay. So what we can do is to do a very calculation when you are in the field. You don't have calculator and all that. So you can just use these two formulas based on the isopoluvial plates that you have. So for 50-year return period, you have 0.7262 area area into L into LC power S is slope and R25 is it's the factor that we can compute from there. So once you just plug in all these values, you will get all these. So if you can see, so this is also a test that whatever calculations that you have done using SUH method are correct. So this is a test for it. If your values coming from these two formulas of 300-year period are deviating from what you have computed from SUH method, it means you have done something wrong. You need to redo all your calculations. So because these are all statistical methods, you need to be sure, you need to be test, and you need to give evidence that whatever calculations that you have done are correct in nature. So suppose if you give me a calculation, I'll just plug in these values, and if they are not coming as per your calculations, I will immediately reject your report. Okay. So for further reading on these methods, what you can do is you can use Applied Hydrology by Venti Chow from Mr. McGraw-Hill. This book is easily available as a PDF format in Google. You just put Google, you will find a PDF. And one of the very popular books that we have all read is Engineering Hydrology by K. Subramanian. So you can refer to these two books, and these are the two manuals that are published by CWC. One is the Estimation of Design Flood Peak in CWC 1973 and Hydrometeorological Zones of India of CWC 1981. So these are our handbooks for hydrology. So when we are trying to do any statistical design methods that we have to understand, these two are our guidebooks. We have to follow these books as it is, word by word. Any deviation from these will give you some numbers, will give you some values, but they will fail in the test. So it is not a good thing that your calculations get rejected. That is not a good thing in the service. So you better follow these rules and come up with a good number so that nobody can question your calculations. Alright, thank you. Any doubts? Yeah, the PPT I will be shared. So we do have a tea break, and what we will do is yes. So what we are going to do is now we are going to practice this method. So so we have a given data that I have given for about 15 years. We have discharge data. Now I want you to use this data and just use a Gumbel method, simple Gumbel method for time now, and compute 25-year, 50-year, and 100-year return. So this exercise that we will be doing hands-on. I have already shown you a So after tea break, we will be using this data set to compute these three returns for the corresponding. Because I don't have other information, we won't be using SUH method for this. SUH method you can practice yourself, given a solved example in Subramania or Venti Chow. Or if you want, I can share with you a solved example for you at a later stage. What is more preferential? Huh? Both. Then I will have to generate some data for it. Okay. So you can start doing this, and in half an hour we will come back to this after a cup of tea to evaluate that what we can do. So you can start doing it. If there is any If it is not clear, let me know. I will tell you what the values are. So you can use this data set. Please make a note of this data set quickly so that I can show you the table that you can use at a later stage. So, वैसे तो आजकल not these days today everything we are using computers, Excel files and all. You can get that. So you can use that technique so it becomes easier. But for this practice, I will recommend that you do it by hand for one time. So at least you will know what you are doing. So in computers become a black box. You put something in Excel, something make 2 clicks, something comes up, but you don't know what is happening. So once you do it by hand, at least you know the procedure, and whenever you're doing it in Excel or any other software, if there is any mistake, at least you will be able to catch. Okay? So please make a note of this. Everybody has maken the note of this data. If there is any value that is not clear, please let me know. I will dictate it from here. Yes, are we done? So everybody has copied the data? Yes. Can I change the slide? Yes. So this is the values for K that you can use. So we need to compute 25-year, 50-year and a 100-year return period. Okay. So you can use this value for the Gumbel's method. Alright, so we'll break for T, and after T we'll continue with Gumbel's method first, and then we'll use the log Pearson method in both ways. So if you don't have any, if you can't see any value clearly from behind, please let me know. I will dictate, or you can just come here and see the value yourself. Alright, thank you. So you can please move in for a T and try to solve this using these two methods to solve our return periods for 25, 50 and 100 years. Alright, thank you.
कहाँ रखते हैं क्या हुआ? लास्ट है क्या? कॉपी कर लो। कहाँ गया? अरे सेंसिटिव, ये देखना, सिर्फ फ्लड पिक किया है और ई क्या ईयर है ना, उसके बाद क्या किया है, टी इक्वल टू एन अपॉन, क्या किया है वो उधर से लो, बढ़िया स्क्रीन ऐसे इधर ही आया है। और क्या है, हो गया इतने में? क्या क्या किया है ये? नहीं ये हो गया, दूसरा आ गया, लॉग पियर्सन आ गया, ये वाला एक तो बीच में है, ये तो वो, ये असेंडिंग कर दिया ना, असेंडिंग नहीं किया है, ये तो डेटा है, इसी में असेंडिंग किया है, ये वाला टेबल में ना, ये असेंडिंग किया इधर, फिर ऑर्डर दिया 1 2 3, और एम एम क्या लिया है, एम नंबर है टोटल 21 ना, हाँ ये कितना है 21, और एन, एन ये है, सबके लिए अलग है, ये एन, ये एम है, ये एन 21 ना, यम, ये यम है, ऑर्डर नंबर यम, मतलब क्या क्या है बहन का, 21+1, हाँ हाँ, ये 21+1+2, चलो हो गया, ये हो जाएगा, इसमें ले लीजिए, इसमें 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 ग्रुप में डाल देते हैं, ग्रुप में डाल दो ना।